Okay, it looks like that was working. Well, I guess a couple. Number one, why can't I get into? The other issue is when I talked to tech support on Wednesday, I told them what I need to do is be able to use the document camera to display documents not only in the physical classroom but on the screen, so that students joining by Zoom can see it. And the technician I talked to then, assuming we were connecting in both directions on communication, I understood him to say that was not possible with the workstation in the classroom. Is that the case? As things are now, I have to carry my own equipment in to make it work. And there's a workstation and a document camera here. So it sure be great if I didn't have to lug those 20 pounds of stuff in. Yeah, right. but obviously something's better than nothing. Okay, we are about ready to start. And I see I have a few people online as well as in class. So if you're attending via Zoom, if you send a text message and just say hello. And if your name isn't automatically on that, then say your name in the message. By default, any message that you send will be visible to everyone. If you have reason to not want that to be, then right in the chat box, you can pull down where it says to everyone. You can that's a drop down menu, and you can send it just to me. Also, please turn on your camera so I can see who's actually here. There are good reasons to go blank for a minute. If you have something going on and you just think it would be distracting to the rest of the classes, or you need to step away for a little while, that's okay. Just to turn it off, but then turn it back on when you get back. And likewise, for anybody in the physical room here, if you need to step away for a while, it really doesn't help to call attention to everybody else and say, hey, I'm leaving for a bit. Just go and then come back when you can. Let's see. Now, if I could get a thumbs up or a audio or something, are you all online able to hear me? Is that working? Okay. I am, for the most part, going to be working from my document camera here, so you'll be able to see that. But I think when that happens, you won't be able to see me, which honestly might not be so bad. I wasn't that good looking when I was young, and I'm not young anymore. So that'll probably improve the class a little bit. But I also don't see you because I'm looking down at the paper. So if what is appearing on the screen at any time is not like I'm writing on the bottom half of the page and only the top half is showing up, please say something. Don't wait to kind of wave your hand around or something, because who knows, it might be 10 minutes before I see you. So I'd much rather just have the auditory signal and just say, please move the page or something like that. Scroll, if you want a single word, I guess that would work. Move. um, so, um, all right, I need to call the roll and see who's here in person. Let's see. And if I mispronounce your name or something like that, please let me know and I'll make a note of it. Charles Bilsma. Chanel Campbell.
Here.
There. Okay. Thank you. Austin, I think it's Doomstra, but I'm not sure.
It's Dimestra, so pretty close.
Dimestra. Okay. That makes sense, actually. Jeffrey Dunst. I'm having serious glasses issues here. I may have to flagrantly break the rules. George Garcia. Dahlia Jersevec. No. Looks like Landisio Jiao. Dustin Matthews. Megan Piantowski. Samuel Swift. Joshua Van Zilt. Micah Vandenberg.
Here.
All right, thank you. And Tommaso Vissani. Yeah, thank you. Okay, anybody I missed? All right.
Yeah, you missed me.
What's your name? Oh, Jack Collins. Jack, I don't see you on my list. Did you sign up a little bit later? Jack, can you hear me? Oh, you're on mute. Yes, I am talking right now. Okay. All right. Okay. First of all, my sincere apologies to the people who were trying to join by Zoom last time and it didn't work. I've actually been on the phone for a lot longer than I wanted with tech support. We thought we had it worked out, and fortunately I came quite a bit early tonight because it wasn't worked out. And this is kind of a patch job here. That's the official way of doing things isn't working still, but it looks like we have at least something working, so that's good. Last time we talked about solving systems and writing solutions, so let me switch over to my document camera if I can. Okay, so we went through this one and solved first three systems of equations because they give us the three cases that can come up. Actually, it was also just for practice to see how to do this on a matrix. This particular one has solution x1 is 1, x2 is 2, x3 is 3. So a unique solution. And then we did a couple more. We did one that had infinitely many solutions, and we talked about how to write the infinitely many solutions in both a parametric form and a vector form. And then we talked about, well, suppose it, what if it doesn't have a solution at all? Well, here would be an example. And the way you recognize that when you're row reducing a matrix is you get zeros in some row except for the rightmost column. And this one says 0 times x1 plus 0 times x2 plus 0 times x3 equals 1, which of course is impossible. So there are no x1, x2, and x3 that will make that work. So that was basic solving equations. And we do that by means of elementary row operations. You can multiply a row by a non-zero constant. You can interchange two rows, and you can add a multiple of one row to another one. And you do that to try to produce row reduced echelon form. This is kind of the classic case of RREF here. Ones down the diagonal, zeros above and zeros below. And that's kind of the first pass of getting started by solving by matrix methods. So is there anything about that we need to talk about? Okay. Yeah. Is there a way to do that in MATLAB? I think you can do that by the way, if you're online, the question is, can you get to row echelon form rather than reduced row echelon form with MATLAB? And the answer might be, did you check to see if there's an REF function? Yeah, there is. I can think of a way to do it, but it goes beyond what we've talked about yet. There's a thing called an LU decomposition. It's a lower triangular matrix times an upper triangular matrix, and you could use that to get the REF. Yeah, it's a great question. And let me, there is something I could tell you though right now. And let's see here. I need to change my screen share so that people online can follow. Is it working? I'm not seeing what I'm supposed to see here. Oh, there it is. Okay. Are people online, if you could answer with voice rather than text, are you seeing an octave? It's like a matrix calculator here.
Yeah, we are.
Okay. So let's just type one in here. 1, 1, 2, 9. So this is to answer the question, can you get to the row echelon form with MATLAB or Octave? And the answer is this would be a way you could do it, which would not go beyond what we've done right now, except that I'm going to show you some commands for Octave that I haven't done before. You can do row operations with Octave. So if you've programmed in any of the languages in the C family of languages, you have this thing where you do like x plus equals 5 and it just adds 5 to x. I'm going to do something like that here. But what I want to show you first is I've got a matrix A here. And if I want to look at the first row, the row comes first and then the column. But if I put a colon in there, it means the whole row. So what I could do here, for instance, I can say, okay, A1 colon, and then I'm going to do actually minus equals whoops, not the 1, it's the 2 I want to modify, right? A1 colon, 2 times that though. Actually, I think this would be better because this is our theoretical construct. Add a negative 2 times the first row. And I got that 0. Then, now that's a pain the first time, but the next time you just up arrow and then you modify it. So row 3, I would like that to be minus 3 times the first row. And I got that. And at this point, if you're looking ahead, you could see that this is not going to produce a unique solution because those bottom 2 rows are the same. But once I see that, then I can get that format by saying, okay, what I'm going to do is take minus 1 times the second row and add it to the third. And I got my zeros there. And now for REF, what I'll do is take the second row and multiply it by 1/2. So there it is. So for a small matrix, that works pretty good. You know, if you had a 25 by 25 matrix, this is going to be no fun. And there's other ways to make it work. Okay, any other questions? All right, we probably better get rolling then on the new material. Let me shrink this and get my document camera showing. So I am now on section 1.2. And it occurred to me that there might be someone here, physically here tonight, who didn't know about the notes if you didn't come the first time or couldn't, whatever the case. I do have a couple copies of the section 1.2 notes if anybody wants it. I have 2 to give away, happy to do it. And if you didn't get the one from Tuesday, I have a few copies are left over from 1.1 as well. So I think it's just easier to dispense with the formalities. If you'd like a copy, please feel free to just step up and take it right now. You don't have to wait. And we'll get going here. Okay. we want to talk about matrix operations and solving systems by an inverse. Now, I wrote this out kind of formally here, but now that I'm in class, it strikes me that there is a lot better ways of doing it. Suppose I had just this example, 2x equals 3. If I wanted to solve this, I could multiply both sides by the reciprocal of 2. And then I get the solution. Now this 2 half times 2, of course, is 1. I'm writing this out in painful detail because that's what it's going to look like with matrices. And then we say, oh, we know what that is. 1 times x is just x. And so we get the solution. So if we could find a way to multiply matrices, and if we could represent a system of linear equations as a matrix multiplication, and if we could come up with something like a reciprocal, then that would be another way of solving systems. And in fact, theoretically, it works. So what I want to do is take a particular example. So let's take this guy right here. And I want to be able to write this by means of multiplying matrices. So the first thing I want you to notice is this. If you just look at this very first row, I have coefficients of 1, 1, and 2. And if I took these two vectors here, 1, 1, 2, and x1, x2, and x3, if I took the dot product, I would get exactly this thing on the left. You get 1 times x1 plus 1 times x2 plus 2 times x3, and that is the left-hand side of that first equation, right? So there's a dot product. Now, what's this? Okay, just by about notation, when we're writing by hand, we oftentimes would write something like this, that A1 dot, you put like a bar over it if you wanted to indicate it was a vector, and the same for the x, and a bar over that. When we're typing, we usually use boldface. So it's just, if you see that, it means generally vector. The meaning of the strange notation A1 dot is this: it's the first row and then all of the possibilities for the columns. So first row, all of the columns gives in the coefficient matrix 1, 1, 2. Okay, and if you wrote out the dot product, which, you know, this all makes sense if someone's working through this when they're not watching me do it in class. Whoops, what am I writing here? 1 times x1 plus 1 times x2 plus 2 times x3. And that's the left-hand side up here. Okay, now if you did something similar with the next two rows, you could set that up as dot products as well. For instance, 2, 4 minus 3. You could take the dot product with x1, x2, x3. And the result would be, it's slow. There it goes. The result would be 2 times x1 plus 4 times x2 minus 3 times x3. And of course, that bottom row could be done in the same way. You just want to have a 0 for your coefficient. All right, so observation number 1, this stuff on the left-hand side could be written as dot products. Observation number 2, we actually have a couple different ways of writing vectors. For this one, for instance, you might see it written this way, or you might see it written this way. Now, it turns out that if you have a matrix with a single row on the left and a matrix with a single column on the right, then the matrix product is just this thing right here that we already did. It's 2 times x1 plus 4 times x2 minus 3 times x3. It's essentially a dot product. Okay, so we're going to be taking, I got to switch hands here. We're going to be taking things on the right. This is immensely difficult. I actually am dyslexic, so I have to make sure I'm not flipping it like twice. My right. Okay, so if I have a column here and a row here, then these are going to tip up like this. And you take the product of corresponding entries, add them up. That's the vector or the matrix product. Okay, so back to this guy right here. What we're going to be doing is we're going to be writing this as the coefficient matrix. And I don't have time to read all of that, so I think I'm just going to go with this, the coefficient matrix. What I'm doing is I'm copying the numbers that are multiplying x1, x2, and x3. And now I'm just going to do what we were doing before, except I'm going to do it for each row individually. So if I take this row multiplied by this column, I will get 1 times x1 plus 1 times x2 plus 2 times x3. Then if I take this row, this column by this row, I'll get 2x1 plus 4x2 minus 3x3. And likewise, I can take this times this. Oops. I was thinking 3 because I just wrote a 3. 3 times x1 plus 6 times x2 plus 0 times x3. And just for good measure, put brackets around it and say that's a matrix. Now notice that's a matrix that has 3 rows for sure, but it only has 1 column. These are not 3 different columns. These things are being added. So that's 1 column. Now, I don't know what I was thinking I was going to tell you all here, but I think maybe that was going into way too much detail. So let me give you another example here, just so you can follow. I'm just flipping over the page. I'm going to take that same matrix, 1, 1, 2, 2, 4, minus 3, 3, 6, 0. And now, rather than x's, I'm going to put some numbers in here. Okay, so I'm going to do 1, 2, minus 1, just so you can see the pattern. So this is, by the way, a 3 by 3 matrix, and this is a 3 by 1 matrix. It's always, when we name them this way, it's the number of rows by the number of columns. It's never the other way around. We never say the number of columns first. We need some standardization. Otherwise, if I said, think of a 3 by 5 matrix, well, everybody would have to ask, well, you want 3 to be the number of rows or number of columns? So we just always do it the same way, rows first, then columns. Okay, so if you wanted to multiply something like this, what you would do is just what we did before. It would be the 1, the 2, and the minus 1 multiply these elements right here. So that's 1 plus 2 minus 2, 0. 2 times, 2 plus 8 plus 3, 11. 3 plus 12 plus 0, 15. Now I want to see the rest of my class. Okay, is this making sense to everybody? All right. Okay, let's carry on then. Now, the next thing I want to talk about, and I think I'm trying to shorten this up because we spent a bit of time getting started here. What if you had a second column here? So you had two columns rather than just one. So I'm going to take the same left-hand side. And now I'm going to take this one again. And I'll put a second column. Well, the way you do that is you just take it a column at a time. You take that first column times this whole matrix. And of course, you do that a row at a time, right? This column times the first row gives the first row in the product. First column times the second row is going to give row 2, column 1 in the product. Third row, first column is going to give row 3, column 1 in the product. So the row number in the product is coming from the left factor and the column number is coming from the right. So, well, we already did this one, right? 1, 2, minus 1, we just computed that. That turned out to be 0, 11, and 15. And now we just do another column. So you take this times this, 0 plus 1 minus 4 is -3. And 2 times 0 is 0 plus 4 plus 6, 10. And then 0 plus 6 plus 0 is 6. So the row number is going to come from the left factor. The column number is going to come from the right. So this thing times this thing should be third row, second column. 1, 2, third row, second column goes right there. And if you just check it out, 0 plus 6 plus 0 is indeed 6. So it worked. Okay. Now, anybody want to ask a question about that?
Little bit you just said. 30 seconds.
The row number comes from the left factor. The column number comes from the right. So if I take row number 3 and column number 2, I'll get the 3, 2 entry here. Okay. So then you just take that dot product and it tells you where to put it. So now we all know this, you know, if once you get used to it anyway, everybody knows it. Take a column from here and a row from here, take the dot product, and you've got an entry in the matrix. Which entry did you get? That would be a good question, right? And the answer is the row number comes from the left factor, the column number comes from the right. Now, there's other ways of thinking about this, and if you're already feeling stressed, ignore what I'm about to say in this next little box, okay? Because frankly, you don't need it right away, and you will figure it out on your own anyway, if you're doing many of these by hand anyway. You could think of it this way. These could be scalars times the columns over here. So this would be the scalar 0 times the first column, plus the scalar 1 times the second column, minus the scalar -2 times the third column. Add those all up and it'll give you this column over here. And that is sometimes quite helpful. Not always, but you know, sometimes it's a good way of looking at it. So, and you know, if you know, I don't know, people absorb things about spatial information at different rates, if that's feeling like overload at this point, we'll just ignore it because frankly, you don't need it. But eventually you'll want to notice that pattern. Okay, let's see if we could do this with a calculator then. And so what I'm going to do is I'm going to the matrix menu here, second matrix, and I'm going to edit matrix A. And I want a 3 by 3 matrix. And I'm going to put in 1, 1, 2, 2, 4, minus 3, 3, 6, 0. So that's matrix A. And I'm going to go back to matrix again. And I'm going to enter matrix B. Whoops, I made a mistake. Oh, I see what happened. Okay, let's just see if I got what I wanted there. 3, 6, 0. I did. Well, what do you know? Okay, second matrix B. I want to edit that. And I would like this to be well, it's 3 rows, but it's 2 columns. And the entries are 1, whoops, 1, then 0, 2, then 1, minus 1, then minus 2. And hopefully, let's just check. We've got what we need for A. And let's see, 1, 1, 2, 2, 4, minus 3. Yep, that looks right. And for B, yes, that appears to be correct. Now, we can ask the calculator to multiply these for us. So all you do is you just use that names menu. I want A times B. And we almost agree. The 11's not right. Okay, well, we just learned how to figure out where that comes from, right? We're interested in this element, and this is row 2, column 1. So that would be from the second row here and the first column here. So let's double check. 2 plus 8, 10, plus 3 is now, just a few minutes ago it was 11, but now it's 13. So there we go. Okay, so that kind of fills in for this. If you read through this, you'll figure out what I was doing. But okay, so what we would like to do now is to write systems of equations as matrix multiplications. So I'm actually going to take this guy that I had before, 1x1 plus 1x2 plus 2x3 equals 9. 2x1 plus 4x2 minus 3x3 equals 1, and 3x1 plus 6x2 plus 0x3 equals 9 once again. If I want to write this as a matrix multiplication, what we would do is this. You write the coefficient matrix 1, 1, 2, 2, 4, minus 3, 3, 6, 0. Then the vector x1, x2, and x3 equals the vector 9, 1, and 9. So this system can be written as a matrix multiplication. And you notice if you tried that thing I was saying earlier, take x1 as the multiplier on the first column, x2 as the scalar multiple for the second column, and x3 is the scalar for the scalar multiple with the third column, you would get just exactly this thing on the left-hand side. You can sort of think of that as x1 times the vector 1, 2, 3, x2 times the vector 1, 4, 6, x3 times the vector 2, minus 3, 0. So those are actually kind of handy ways of looking at that. You can also do that same trick with rows, but right now it isn't helpful. So we'll do that another time. Okay, so official definition now. The coefficient, well, the matrix form of a system of equations. Suppose we had this system here. Now let me see, I'm supposed to get m equations and n unknowns. So A11 x1 plus, remember now, row first, then column. A12 x2 plus A13 x3 for however many terms you have. If we're going to have n unknowns, we're supposed to end with xn, and the this will still be in the first row, right? So that's got to be an A1, and then it'll be in the nth column, so that's got to be 1n. And that is the right-hand side. Traditionally, we use B's for that. And then similarly, this one looks like A21, A22, A23, A2n, and you keep going until you get to the last one. And this says there's supposed to be m equations, so that'll be am1 x1 a plus am2 x2, and the last one is amn xn equals, oh, and I made a mistake last time. To n. So what's the coefficient matrix? Coefficient matrix looks like this. A11, A12, A1n, A21, A22, A2n, and on down to AM1, AM2, AMN. And if you wanted to write out the whole system, I said here in the notes, the coefficient matrix is, but the matrix form for the system equations is next. You could just get it here. X1, X2, Xn equals B1, B2 through Bn. And I did it that way because I didn't want to copy all that again. This guy right here, this is the coefficient matrix. And that whole equation is the matrix form of the system of equations. Traditionally, we use capital letters to indicate matrices. You know, you don't actually have to, but it's the tradition. So this is A times the vector X equals the vector B. And that extra squiggle there on the vector mark was not intentional. Okay. So that's the vector matrix vector form. If you spelled it all out in terms of the entries in the matrix, it would look like that. And you can see a particular example by looking at this one right here. And this is actually kind of the standard way we're going to be doing it from now on. All right. Actually, I did something like this earlier, right? So I guess we could skip at least one of those. Products of matrices. Suppose you want to multiply these two matrices right here. Let's do that one and then call it good. You'd have 1 times 1 times, whoops, 1 plus 1 minus 4, 2 minus 4, negative 2. Then 2 plus 4, 6, plus another 6, 12. And then 9, I hope. Now, these all can be done on Octave as well. And it's good to, or MATLAB, you know, whichever one you're working with. So let me pop that up and do that. By the way, CLC means clear command. It's a kind of a handy command to have available. So A is going to be this matrix. Do I already have that one in, by the way? Nope, I don't. So there's my matrix. I want to multiply it by this thing, which I'll call X. Actually, there's a little trick here. You could enter X as put in -2, then hit return, etc. But there's a way to make it do those all at once. Just put a prime mark after it. And then if I take A times X, oops, lowercase x, did I enter the wrong X? I did. Oh, I entered the product. Try again. -2, 12, and 9. So that works. And in the same way, you can do larger products with Octave or MATLAB or your calculator. So let me put in one more. I am moving down to just above where it says summary of products. There's an example there. So I'm entering that right-hand matrix. Rows 1, 2, 0, 1, -2, 1, and -2, 0, 1. So if I take A star B, there's my product for that matrix. And, you know, obviously that's way, way faster than trying to do that by hand. Okay, any question about matrix multiplication up to this point? I'm just curious, how many people have done this before? Multiplied matrices or no? Okay, not much. Oh, someone speaking out here. Okay. Well, let's go to the summary then. And then I want to talk about some properties of matrix multiplication because they aren't nearly so nice as the real numbers. And that's too bad, but that's the way it is. Okay, summary of products of matrices, of course. The number of columns of the left factor, actually, that's not true. Oh, I see. It's something different. The number of columns of the left factor must equal the number of rows on the right, and that is correct. So let's take a look at this one, for instance. This is a 3 by 3 matrix. This is a 3 by 1 matrix. Those two sizes have to agree. If they don't, you cannot do the multiplication. Because if you think about it, you want to run down this column and across this row, right? So the total number of things in this row, that's the number of columns here, must be the total number of things in this column, which is the number of rows in the one on the right. So that has to agree. The product matrix has the same number of rows as the left factor and the same number of columns as the right. So this one, for instance, is 3 by 3. This is 3 by 2. Those two have to agree or the product is undefined, but then the resulting matrix is going to be a 3 by 2 matrix. So in a certain way, those inner dimensions there, they kind of get used up in the process of doing the calculation. And so we could look at something like this, for instance. This is a 3 by 3. This is a 3 by 3. And without doing the calculation, we can tell this. First of all, the product is defined because those inner dimensions match. And the resulting matrix will be 3 by 3. So I don't really need to do the whole calculation in order to predict whether it's going to be possible. And secondly, what size I'm going to get at the end. Okay. And that really is useful. Because so often, you know, the first question is, well, can I multiply these things? And if the answer is no, then you shouldn't spend a lot of time working out arithmetic, right? Okay, some vocabulary. We talk about the dimension of a matrix is 3 by 2 or 3 by 3, etc. And when we say dimensions, plural, we usually are meaning to kind of focus on the individual pieces. So the dimension of the matrix is 3 by 2, or what are its dimensions? 3 and 2. It means roughly size. Okay, the strange world of matrix algebra. First of all, scalar multiplication. If you take any matrix whatsoever, so I'm just picking stuff at random here, and I pick any scalar, no matter what, well, how about something that's not too hard? 2. I can always multiply a matrix by a scalar. And it's just like you did with scalar multiples of vectors, say in physics or multivariate calc. It's 2 times every single entry in here. So 2 times 3 is 6. 2 times 2 is 4. 2 times minus 4 is minus 8. 2 times 2 is 4. 2 times 0 is 0. 2 times 9 is 18. So, and the key here is any and any. Any scalar times any matrix is always defined, and it's done in that kind of way. Okay, can you add 2 matrices? The answer is yes, as long as they have the same size. So this is a 3 by 2 matrix. I can add it to any other 3 by 2 matrix, And in this case, because it's clearly not random, I've chosen the negative of that one. And if you add this up, you get a bunch of zeros in here. But you know, don't make the mistake of saying, what's the result? Oh, it's 0. No, 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 no. This is a scalar. This is a matrix. So those two are not equal. Although sometimes people will write this one, so this is equal. You know, if you got a 25 by 47 matrix, you really don't want to write all those zeros, right? So people will indicate it this way. They will say, it's the 0 matrix of dimension 3 by 2. And that's fine. No one is going to complain about that. Another way they'll write it is just, I don't know. Well, when you're typing it, you could do it as boldface and then put the dimension on there. Okay, how would you subtract two matrices? Well, in the same way that you do with real numbers, really. If you take like an abstract algebra course, you find out that we don't really think of the real numbers as having when you get to theoretical mathematics, we don't think of it as having 4 operations: addition, subtraction, multiplication, and division. No, it has 2 fundamental operations: addition and multiplication. And what do we mean by 3 minus 2? Well, what we mean is 3 plus the negative, the additive inverse of 2. So you do the same thing with matrices. If you wanted to subtract these matrices, well, you could think of it if you wanted to. I don't want to be too inventive because it takes too long. If you wanted to subtract these, you could just subtract the corresponding entries. But to formally define it, what you're really doing is you're adding the negative of that matrix. And by the negative, I mean you multiply it by -1, just like you could multiply it by 2. So I set that up so I could go fast. 1, 0, 0, 2, -1, 0. Subtract corresponding entries or add the additive inverse of the left entry to the right entry to the one on the left. Multiplication of two matrices, well, they have to be of compatible dimension. So it is not true that if you pick two matrices, you can just pick them at random, that you can automatically multiply them. No. So for instance, if I do this, 2, 1, 3, 4 times 1, 2, 3, that product is not defined. Why? They have incompatible dimensions. This is 2 by 2. This is 3 by 2. Those inner dimensions disagree. So you can't do the multiplication. Otherwise, if they do agree, then you do just what we said before, right? So, and there is an official definition for it. I'll just write this. This is how I was taught. Let's see. It won't make sense unless I write the whole equation. The matrix with entries Aij times the matrix with entries B ij is equal to the matrix whose entries are, well, it's a sum. You're going to take a dot product, right? It's Aik Bkj, where K goes from 1 to, well, they have to say what these dimensions are. N by M, M by R, M. And so there's a formal definition, but honestly, in this course, we're not trying to get everybody to become a theoretical mathematician. We're mostly trying to get you to where you can use this stuff. So that's probably the first and last time we'll talk about that. Okay, the zero mention matrix of dimension nm, it could be written in various ways, but I mentioned this before. It just means you have an n by m matrix, all of whose entries are zero. And by the way, in the algebra of matrices, that's the additive identity. Take any matrix, and as long as you pick the zero matrix of the same dimension as the original one, you could add that zero matrix on the right, or you could add it on the left, and you just get back to the original matrix, right? So that's the additive identity. And the question is there a multiplicative identity? And the answer is yes. And it's particularly simple. So what I'm going to do actually is I'm just going to show you one, and then you'll see it. Then I'll give you a formal definition. What I'm going to do is put ones on the diagonal and zeros everywhere else. Now let's do the matrix multiplication. Well, that first dot product would be 2, 3 minus 1 times 1, 0, 0. It's just going to pick off that 2, right? The next dot product is going to be 2, 3 minus 1 times 0, 1, 0. It picks off the middle piece, the middle entry. And likewise, this one, take the dot product with this, it'll just pick off the last one. And notice we get that row back again. Likewise, now I'm going to go for the second row. This times this is 4. 4, 6, 7 times dot product with 0, 1, 0 is 6. And 4, 6, 7 dot product with 0, 0, 1 is 7. You get this thing back again. And this is 2 by 3. This is 3 by 3. And so those agree. The multiplication is defined, and I got a 2 by 3 matrix as advertised earlier. And it always turns out that way. The n-dimensional identity is this. It has ones on the diagonal and zeros everywhere else. Little catch here, though. Notice that the thing you multiply on the right to get this original matrix back and the thing you multiply on the left would have to be different, because this is 3 by 3. If you put it over here, a 3 by 3, the 3 and the 2 don't agree. So you couldn't even multiply then, right? So what did I have here? 2, 3 minus 1. I'm just going to flip this over. 2, 3 minus 1. And 4, 6, 7. If I wanted to multiply a matrix on the left to just get this matrix back again, oops, then I would have to have, well, this is a 2 by 3. I've got to have a 2, and the identity matrices are always square. The number of rows and columns are the same. So I've got to have a 2 by 2 identity here. And now this will work. If I take this times this, I'll get 2 plus 0, first entry, 2. Then if I take this column, I'll take 1 times 1 plus 0, 1 times 3 plus 0, and finally minus 1 plus 0. I get that first row back. And now when I take these times the second row, it picks off the second element, 4, 6, 7. And if you check these with your calculator or Octave, you'll find out they agree. So the point is, let me give this a name. A, which is a 2 by 3. What we've shown is that if you multiply it on the left by I2, you get A back again. If you multiply it on the right by I3, you get A back again. So is there a multiplicative identity for matrices? Yes, but it's a little more subtle than with real numbers, right? If you just take any old real number, multiply it on the left or the right by 1, you get the real number back again. So 1 times 5 equals 5 times 1 equals 5. But with matrices, you do have a multiplicative identity, but it's might be a different one for left multiplication than it is for right, depending on the size of the thing you're starting. And if you're used to real number arithmetic, and we are, that seems strange. You know, shouldn't you just have like a 1 matrix that, well, you don't. Matrix multiplication is not commutative. So what do I mean by commutative? Real numbers, you can multiply them in any order. 2 times 3 and 3 times 2 are both 6. Does that work for matrices? No. And as a matter of fact, if you just pick a couple of simple matrices, it's almost always not going to work. So whoops, I don't want an equal sign here. I want to multiply this by something. How about this? So let's take this product. I'm going to get what? 1 plus 4, 5. And then take this product, 1 plus 0, 1. Then I'm going to get 1 plus 2, 3. And 1 plus 0, 1. Okay, that's putting them in this order. If I put them in the other order, 1, 1, 2, 0, 1, 2, 1, 1, multiply those out, well, I'm going to get 2, 2. And what this does is it doubles the first column and then adds the second column. So 2 and 1 make 3 and 4. And as you can see, those things are not equal. That's the weirdest not equal sign, but anyway, switching the order typically will give a different product. Not always, by the way. And so you'd think, well, at least you can depend on it. It's going to be different. Nope. Sometimes it's the same. So for instance, if you took this one here, multiply it by the left on the left or the right by I2, the 2-dimensional identity, you'd get it back again. So, you know, that one works. They do commute, but not all of them do. And most of them actually do not. So let me give you an example. It turns out, by the way, that any diagonal matrix, diagonal means this, has zeros off the main diagonal. Any diagonal matrix will commute with any other matrix. So if I multiply this out, let's see, I'm going to get that, I think. And if I do it the other way around, well, I'm going to get, did I make a mistake there? What? That doesn't make sense. I didn't get the same thing. Well, rather than spend a bunch of time here, I think there's actually a bug in my calculation. But to give an example, which surely is correct, if I multiply on the right or the left by I2 for this matrix, I get the same result. So that would be a pair of matrices that do commute. So matrix multiplication is not commutative in general, but there are certain matrices that will commute. Also, there are examples of what we call zero divisors. And let me give you an example if I can quickly. Actually, that will work. And, oh, those are the same. Well, okay, I made it easy. So this is a non-zero factor, and this is a non-zero factor. But if I multiply them together, I get a zero matrix. That cannot happen with real numbers, right? If you have x times y equals 0, then either x is 0 or y is 0. But with matrices, not true. A times b can be 0 when neither a nor b are 0. All right, now, is there a multiplicative, and nobody says this, but I'll say it once. Is there a multiplicative inverse of a matrix? The answer is that some matrices have a multiplicative inverse and others do not. This one is supposed to be cooked up ahead of time. And what I mean by multiplicative inverse is this. Let's take, I'm just copying this right now. Let's just take real numbers. Is there something I can multiply 3 by to get to the multiplicative identity? Well, sure, I can multiply it by a third, right? A third. And so you could say 1/3 is the multiplicative inverse of 3. Or you could say that 3 is the multiplicative inverse of 1/3. That's both of those are true. So is it the case that you can always multiply, given a matrix, can you multiply it by something that will get to the multiplicative identity? In other words, the IN for the appropriate n. And the answer is, in this case, you can, if I've done it right. Let's see, we got 6 minus 5 is 1. So far, so good. Minus 3 plus 3 is 0, looking hopeful. 10 minus 10 is 0. And minus 5 plus 6 is 1. Woohoo! This is I2. And I will just tell you right now that if you flip these around, you'll get the same thing. I'm not actually computing it. I'm claiming it, but it is true. Whoops, I wanted it in the other order. So yes, this one has a multiplicative inverse, and we label it as A inverse, just with an exponent of -1. If you want to prove that two matrices are multiplicative inverses, The official version of the proof would be this. If let's give this a different name for now. I called it B inverse, but that's claiming what we're trying to prove. How would I prove that C is B inverse? So it would be a question. Well, what I would do is I'd multiply B times C, and I'd multiply C times B, and I had better get, in either case, the identity. Furthermore, I better get the identity of the same size, which means this, that these original matrices must have started as square. Because if they aren't, if you flip their order around, even if the multiplication is even defined, if it is defined, you'll get a different size. So let's see. Suppose I had a matrix. Well, why am I writing that? Not helpful. D, which is a 2 by 3, and E, which is a 3 by 2, the resulting matrix would be a 2 by 2, right? But if I flip them around, E, 3 by 2, times D, 2 by 3, the resulting would be a 3 by 3. And so if this thing is going to work, both of these must be square, and they must have the same dimension. So that's a necessary condition for having a multiplicative inverse. It's not sufficient. There are lots of square matrices who do not have multiplicative inverses. Okay. Well, that's saying a lot, but that's different from teaching a lot. Is there any question up till here? Anything we should go over? In a nutshell, there is an algebra for matrices. It's not nearly so nice as the one for real numbers. Okay, now, if you do have an inverse, however, you can solve systems of equations by means of an inverse. So let's kind of walk through a couple of these. I'm going to use technology though, because it's faster, and while I do want you to learn some skills to do things by hand, most of the time, once we've learned the patterns, we will do stuff by calculator or MATLAB or whatever with technology. So let's get the inverse of this matrix, or find out it doesn't have one. So what I'm going to do is go to the matrix menu, and let's see, how about if I just do a new one? I'll edit C, and I want that to be a 2 by 2 matrix, and 3, 1, 5, 2. Then, if I go back to the matrix menu, I can ask it, does it not have inverse? Oh, it does. I remember now. You have to get it in an awkward way on a calculator. We can do this. That's matrix C, and then I'll just press this inverse key here, and I think that will do it. Woohoo! So let's check it out. Is it true that 2 minus 1 minus 5, 3 times 3, 1, 5, 2 is the 2 by 2 identity. Well, 3 minus 2 is 1. Good start. 2 minus I flipped the entries. See, this is 5, 2, and I wrote 2, 5. Okay, one more time. 6 minus 5 is 1. Good. 2 minus 2 is 0. 15 minus 15 plus 15 is 0. And minus 5 plus 6 is 1. It worked. So if we're going to call this one A, then this one would be A inverse. Okay, here's the idea. If I take 3, 1, 5, 2, multiply that by x1, x2, that equals, I'm going to leave some space here, 1, 3, that's my system of equations. Now, what if I multiply it on the left by the inverse matrix? 2 minus 1, minus 5, 3, and then the same thing here. Now, when I multiply these two together, I just did that up here, right? I get the 2 by 2 identity. Here, you actually have to do some work. It'd be 2 minus 3 is negative 1, and minus 5 plus 6 is plus 1. And now what's going to happen when we multiply x1, x2 on the left by the identity? Well, we get x1, x2 back because it's the identity matrix. So minus 1, 1 is supposed to be the solution to this system. Except it isn't. Get some help from the calculator. Okay, so that worked. All right, so our B is 1, 3. Well, this works now, but I'm trying to figure out what went wrong. Excuse me? Mm-hmm. Okay. Okay. So anyway, the answer is it does work. You can solve this system by multiplying this right-hand side by the inverse of this. X equals the inverse matrix, which is 2 minus 1 minus 5, 3 times this B matrix 1, 3. And you get minus 1, 4. Okay, let's do this one, but I'm going to flip over on the other side. 1, 2 minus 1, 2, 2, 1, and minus 1, 1, minus 1. That times the X vector is equal to 0, 3, minus 2. So how would you solve this by inverses? Well, let's get some notation here. This is, we'll call that the matrix A. The vector X is equal to the matrix B. If you wanted to do this by inverse, it would be this. X equals A inverse times B, provided that there is an inverse. And of course, not every matrix has one. So let's see if we can find it. And we're getting so much junk in here. I think I am going to just go back to A. 3 by 3. Okay, 1, 2, minus 1. 2, 2, 1. Minus 1, 1, minus 1. Okay. So there's my matrix A. And what I want to do is compute A inverse B. So matrix A, take the inverse. Oh, I didn't enter my B yet. And that is 0, 3, minus 2. Okay, then I can take A inverse times the B matrix, and we get 1, 0, 1. And let's just check, is it right? It is. If you multiply 1, 0, 1 times this matrix, it takes 1 times the first column, plus 0 times the second column, plus 1 times the third column. So it adds the first and the third. Add those, you get 0. Add those, you get 3. Add those, you get minus 2. It worked. So if a matrix is invertible, then AX equals B implies that X equals A inverse B. So if you can get the inverse, that is a way of solving a system of equations. Now, let me just mention that for small matrices, or when you're doing theory, so you're trying to come up with a formula, you're not necessarily trying to do calculations, this is true and sensible to do. If you are looking at a real world 2500 by 2500 matrix, do not try to solve it this way. This is numerically unstable. Mathematically, the statement is true. But when you go through all the calculations to get the inverse, you're going to have so much round off error. You don't want to do it that way. So, for a 3x3, it's absolutely no problem. For a small matrix, this is okay. For theory, very helpful. And, you know, occasionally we'll use the inverse, but for large systems solved numerically, this is a bad idea. So you should not try to solve large systems numerically this way. Now, it might work. You know, you might be lucky, and it's what we call a matrix is well conditioned. It might not produce a lot of round off error. It might be fine, but you just don't know. That's the issue. Okay, now there is an algorithm for computing the inverse, and there's more than one. Here is one that you could actually make sense numerically, though. There is a formula as well, but the formula is horrendously complicated. We haven't got to all of the stuff. So I just want to tell you this one way. And this is a way you could do it by hand, only I'm going to sort of do it by hand and sort of do it by calculating. Suppose I wanted the inverse of this matrix, or I want to know that it doesn't have one. So one of the two, and I don't, maybe, you know, I don't have this calculator available. I don't have MATLAB available. What could I do? The answer is this. If, first of all, you know, it's got to be square, or it doesn't have an inverse. Only square matrices have inverses. So you put the corresponding size identity over on the right here. You just append the rows of the identity to the rows of the matrix. So I actually have a two matrices pasted together to make my new matrix. Then I compute the row reduced echelon form of this. And what will I get? Well, one of two things will happen. Number one, I could get one or more rows of zeros on the left-hand side. If that happens, the matrix on the left does not have an inverse. But if it doesn't happen, then I'll end up with the identity on the left, and I'll end up with the inverse on the right. So let's just try it on this, and we'll find out in a big hurry whether this has an inverse or not. And then we can check it with the calculator's way of computing inverses as well. So I'm going to go to A here, and this is going to be a 3x6 now. Okay, so I want 1, 2, minus 1. And then 1, 0, 0. Then 2, 2, 1. And 0, 1, 0. One thing I don't like about the calculator is once the matrices get big, it is awfully hard to see what's going on. So I'm going by memory, not by the screen. But then I will print it out and make sure that I got what I wanted. Okay, 1, 2, minus 1, 2, 2, 1, minus 1, 1, minus 1. 1's down the diagonal, 0's off. So here's my I3 over here. Here's my original matrix A. Then I will compute the row reduced echelon form and I think I would like this to see if we can get fractional form here. Okay, so what I got was, well, first of all, I got I3 on the left, but this is 3/5 minus 1/5 minus 4/5 minus 1/5, 2/5, 3/5 minus 4/5, 3/5, 2/5. And of course, you could write that with a scalar multiple, be way nicer. It's 1/5 times the matrix, 3 minus 1 minus 4, minus 1, 2, 3, minus 4, 3, 2. And we think that this is supposed to be the inverse. And it is. Now, if you start with a matrix that's not invertible, you would be alerted to the fact, because in this left half of the matrix, you would not get to the identity. You'd get one or more rows of zeros. If that happens, then it's just like when you get a row of zeros and something that's non-zero on the other side for a system of equations. It's just, there's no solution. Okay, finally, we get to the null space of a matrix. So let me tell you, I'm just going to flip over and do it by example first. Let's pick a non-zero matrix. Yeah, of course, it could be a zero matrix too, but how about this? This is my matrix A. And I want to just observe this, that if I put a 1, 1 here, I get the zero vector. And of course, it's easy to see that. I cooked this up to make it easy. This column and this column are negatives of each other. So if you add these up, which is what this says, you get 0. So we say that this vector here, 1, 1, is in the null space of 1 minus 1, 2 minus 2. So X is in the null space of A. Are you all familiar with the set notation? And this is element of. So like 2 is an element of the set 2, 3, 4. 2 is in there. So X is in the null space of A if and only if A times X is a zero vector. And in this particular case, if we call this matrix here A, the null space of A is this. It's all vectors that have this form. You can have any entry you want in here, just so long as you have its negative here. No, actually, they need to be the same, just the same entry. K is any real number, including 0. 0 would be fine. So what is the null space of a matrix? It's a set of all vectors that have this property. A times X is the zero vector. And that is what this says. The null space of A is the set of all vectors X satisfying A times X equals 0. And those are boldface, hard to see in the printing, but those are vectors. Now, the null space, it's called a space because it has the property of being closed under addition and scalar multiplication. And what I mean by that is this: we have something definite here. So I'm saying take any old vector you want, just so long as the first and second entries are the same. That's in the null space. Now let's take another vector that's in the null space. How about this one? I'm trying to choose more or less at random. If you add these up, you'll get another vector that's in there, right? So take any two things in here, add them together, you land in here again. Likewise, you take anything in this null space and multiply it by any scalar. Well, once again, you get something that's back in the null space. So this is not just a set. It's what we're going to later on, we're going to call it a subspace. And what we mean, at least part of what we mean by that is, once you have some things in here, if you take a couple of them and add them up, you get another thing in there. Pick any vector in here, multiply it by a number, you get yet another thing in here. So now this actually gives us the ability to talk about counting solutions in some non-trivial way. So I'm just wondering how much of this I want to say. Okay, let me put this one off again. Okay, this page 10. I'll come back to that because I really do want to summarize properties of matrices. And rank. Okay, here's what you need to know right away. Number one, the properties of matrix algebra, we're going to kind of model them on the properties of real number algebra. So I'm not going to go through all of this stuff, but these are the rules that real number arithmetic, or you could say real number algebra, satisfies. For instance, if you have any two real numbers, x and y, you can add them up. There is a sum. Any two real numbers, you can multiply them too, for that matter. There is a product. They have an associative property. If you take x plus y plus z, it does not matter if you add x and y first or if you add y and z first. It doesn't make any difference. You get the same result. And they have a commutative property. X plus y and y plus x are the same. So there's a whole list of these things that are true for the real number system. And, you know, if you want the full list, it's right here in the notes. One of the reasons for notes is so I don't have to write all that down. Now, for matrix algebra, it's similar, but not the same. If you take any two matrices, so that was real numbers on the previous page. Now we're talking about matrices. If you have any two real numbers, you can add them together. Is that true with matrices? No. They have to have the same dimension. So there's actually a restriction even on addition. Can you always add two matrices? Well, if they're the same dimension, you can. Matrix addition, when everything has the same dimension, assuming that both sides are defined, then these will be equal. It is associative. A plus B plus C, it doesn't matter if you do A plus B first or the B plus C first. It'll be fine either direction, okay? Commutative property, that works for addition. It does not work for multiplication. So there is no commutative property for multiplication. There is one for addition. The zero matrix, it's the additive identity. If you add it on the left or the right to a matrix A, you'll get A back, assuming you start with appropriately sized zero matrix. Multiplication is not nearly so nice. For some pairs, A times B is B times A, but for most, A times B is not B times A. In fact, it's entirely possible that A times B is defined and B times A is not. So be aware of that. There is a multiplicative identity. So I times A is A times I. is A, but those i's may be different if you're multiplying on the left or the right, just because they have to have a different size. The pattern's the same. One's down the diagonal, 0 off. But if you had like a 3 by 2, then if you multiply on the right, you got to have a 2 by 2. If you multiply on the left by an identity, you got to have a 3 by 3. So those are different. And then finally, the inverse of a matrix, first of all, no matrices that are not square have inverses. None of them. It must be square to have an inverse. But even if it is square, it need not have an inverse. But if it does have one, then it will satisfy this equation. A times A inverse equals A inverse times A is the identity of the same size as A is. There are distributive laws, and they do work. So as long as the addition and multiplication is defined, A times quantity, B plus C, is the same as AC plus BC. Scalars distribute, as you would expect. Matrix multiplication over scalars, that distributes as well. Notice how complicated this gets. These are all distributive laws. Where with real numbers, you say what? K times quantity, A plus B is KA plus KB. That's all there is to say. With matrices, not so simple. Finally, the rank of a matrix. The rank of the matrix, one way of defining it, it's the number of non-zero rows in its row-reduced echelon form. A matrix has an inverse, an n by n matrix has an inverse if and only if its rank is n. So if you row reduce it, find its RREF. If you get the identity, it has an inverse. If you can't get to the identity, it does not have an inverse. So one of those rare cases in linear algebra where we have a simple rule. What matrices are invertible? Those whose row reduced echelon form is the identity. If a matrix has an inverse, we call it invertible. And you actually are asked in the, I put a little argument in here because I wanted you to see an example, but let me just do one live for you. Suppose I had B, let's call this one a 2 by 3, and C was a 3 by 2. Now, you could ask the question, is this product defined? The answer is yes. It would be something, which is a 2 by 2, right? And okay, so then you could ask, well, what if I turn them around the other direction? C times B. Then would this be defined? Well, answer yes, because these match, right? But let's call that E. That one is a 3 by 3. So is it always the same? Is it always the case that BC and CB have the same dimension? No. And here would be an example to show that, right? And I don't really have to tell you what the matrices are. All I got to do is tell you what the sizes are. And you can see that. So here are some ways that you can argue in very simple arguments that don't go into immense amounts of detail. And you'll encounter some things like that in the homework. Here is a theorem that's going to come up over and over again, and it's starting to touch on the richness of linear algebra. Up till now, this has just been a bunch of rules about how you do this, how you would do that, and kind of by my way of thinking, it's drudgery. But it's the, well, if you've ever had the experience of learning another language, you first of all have to learn vocabulary, you have to learn grammar, and you have to learn syntax, and you got to learn to pronounce it at least well enough so people can figure out what you're trying to express, right? And that's kind of what's happening here. We're learning this grungy stuff at the base of linear algebra, but it's about to change. And here is an example. This is a classic theorem from linear algebra. The matrix, it says that these 7 statements are equivalent. In other words, if any one of these 7 is true, all 7 of them are true. If any one of the 7 is false, all 7 of them are false. And this one is a little ahead of its time. We haven't even talked about what det A means, but we will next time. So suppose A has a multiplicative inverse, then it must also be true that the row reduced echelon form of A is an identity matrix. It must also be true that the system of equations AX equals B has a unique solution no matter what B you put on the right-hand side. It must also be true that the homogeneous equation AX equals 0 has the trivial solution 0, 0. The null space of the matrix A is the single vector, it's the 0 vector. Nothing else is in the null space. The rank of A is n, and this says the determinant of A is not 0. If any one of the 7 are true, all 7 are true. If any one of the 7 is false, all 7 are false. So we're actually starting to build up a little bit of theoretical structure. And the reason we're doing it is it's useful. It's not just entertaining. You could say this backwards. The non-invertible matrix theorem, this is logically equivalent to this. So you will not find this in any formal book on linear algebra, but it's a true statement. And I want to point out that these statements are equivalent as well. A inverse doesn't exist. Well, the row reduced echelon of A cannot possibly be the identity. It's got to have a row of zeros. For every B, AX equals B has either no solution or infinitely many. It can't be unique. If A inverse doesn't exist, then AX equals 0 has infinitely many solutions. In other words, there's infinitely many vectors in the null space. So this and this really say the same thing, but sometimes in applications, it's actually nicer to think of it in this way. Okay, just a quick reminder. When you check the Blackboard course, you will see there's a hand-in assignment. If you are coming to class in person, I would very much appreciate getting that on paper. If you are attending remotely, or if you are attending remotely on Tuesday, then it is fine to work that out by hand and scan it and email it to me. Down here and on the left a ways. Sure. I will be monitoring email, but also over the weekend, I sometimes don't watch it too closely. So if you check the syllabus, my phone number, the number for this phone is in there. So if you need to ask a question, it's pretty hard to ask a question by a text message or something, but you could do something like send me a text and say, hey, I sent you a question by email. Would you mind taking a look? And when within a reasonable amount of time, I'll get at it. Okay. I am sorry that this is kind of a laundry list of stuff about matrices at the beginning. By my way of thinking, it gets a lot more entertaining, but we do have to march through this introductory material because it's the essence of what we it's the computational part of what we're going to be doing for a lot of the semester. Okay, I wish you all well, and I'll see you on Tuesday, and who knows, maybe be chatting with you by text or email or some such thing before then. Oh, it's the same. Yeah. Yeah.
Yes, if we can.
See, so you just look in some of these handouts in the file name, it says with HW, means the homework is in that file. And sometimes it's a separate file. It's just the way that the files have evolved. It's not anything different.
Okay.
So the exercises at the end might be called homework, might be called problems, might be called exercises, all the same.
Okay. Thank you.